Hello, everybody. Welcome to the Evolution Seminar Series. Today, we have a tag team presentation by Matthew Maxwell and Dr. Elliot Sober. Matthew Maxwell is a PhD student here at UW-Madison in the Department of Philosophy. And Dr. Elliot Sober is a professor here at UW-Madison, also in the philosophy department. And today they will be giving a talk titled Gradualism, Mutation, and Natural Selection, Darwin, Fisher, Kimura, and Connecting the Dots. So thank you and welcome.
Nice to be here. This isn't working. Okay, so here are the three isms that we're going to be talking about and how they're related to each other. The formulation of gradualism you see on the screen is a first approximation. We'll refine it, and in fact, one of the main take-home messages is going to be that there are really two logically independent ways of thinking about what gradualism is as a thesis, and it matters because one of them is false. The thing about selection, that's a quote from The Origin of Species, page 6. And finally, there's the idea that mutations are random. So that's our big question. Take the thesis about natural selection and some appropriate formulation of what gradualism is, and also some understanding of what it means for mutations to be random. And the question is whether the natural selection idea plus the mutation idea of randomness gives you a justification or entails gradualism. What did Darwin mean by the idea of random mutation? This is one of the most beautiful metaphors or analogies in Darwin's corpus, and there are several that are really great. He says, let an architect be compelled to build an edifice with uncut stones fallen from a precipice. The shape of each fragment may be called accidental, yet the shape of each has been determined by the force of gravity, the nature of the rock, and the slope of the precipice, events and circumstances, all of which depend on natural laws. But there is no relation between these laws and the purpose for which each fragment is used by the builder. In the same manner, the variations of each creature are determined by fixed and immutable laws, but these bear no relation to the living structure which is slowly built up through the power of selection, whether that be natural selection or artificial selection. Here's a way of capturing the essence of what Darwin's saying here. The black dot represents the blood pressure that a particular organism has, and you can think of a mutation occurs affecting blood pressure. It might move it to the right, it might move it to the left, maybe with equal probability, maybe with unequal probability. It may be that a step to the right is a bigger step in terms of distance than a step to the left. Maybe, maybe not. That's not what Darwin is talking about here. What he's saying is the probability of changing left, changing right, and the magnitude of those changes does not depend on what's optimal. If O1 is the optimum, the organism doesn't start having mutations to the right more often than mutations to the left. It would be the same mutation properties and magnitudes if O2 were the optimum. Why was Darwin a gradualist? That's kind of a hard question. He gives all sorts of different statements about it. And one of them, it seems like a metaphysical article of faith that he thinks that unless you embrace gradualism, you can't be a serious scientist. It's a field of endless, useless speculation otherwise. At other times, he seems to think that Lyell's geology, which was gradualist, is somehow a justification of being a gradualist about evolution. I mean, how close a connection is that? And most telling, Matt and I think, is what he tells us about plant and animal breeding. This is one of several quotations. And he thinks he can see that, he didn't use the word mutation, that mutations are small in their phenotypic effect. And that's how plant and animal breeders are able to modify domesticated organisms. And somehow that fact about artificial selection tells you that out there in nature, evolution is going to happen by the same kind of small steps, one at a time thing. You might wonder whether that's a compelling argument. Here's an idea from Fisher's famous geometric argument, which well, actually, Matt will be the one who does. I'll do some of it, and Matt will continue with it later. But after he does with the mathematical stuff, he proposes an analogy. He talks about taking a microscope and randomly changing some adjustment. And it's suppose the microscope starts off as pretty well in focus, and you're just going to change the dials and settings at random. And his point is, and it's a very intuitive point, that a big random change is more likely to louse things up than a very small change. And as you make the changes smaller and smaller, he says the probability of it improving is about a half. Why didn't Darwin think of that? Darwin knew about William Paley's analogy with the watch found on the heath. He read that as a student at Cambridge. He found it delightful. Why didn't he use that as an argument for thinking that nature is like that, that mutations are likely to be advantageous to the degree that they're small? He doesn't do that. He could have. Okay, here, let's start with Fisher's argument. X is the location of an organism, and we're going to imagine that we're going to compare a small mutation to a large one. That's what these two circles represent. And Fisher's idea of what's going on here is you have a small mutation. What will happen is that the organism will move from its location X in phenotypic space to someplace on that broken line. Whereas if it's talking about a big mutation, it's going to move from X to somewhere in that larger circle. And here, let's get clear on what he means by mutation being random. It's really different from Darwin's. What he means is if the organism is at the black dot under Fisher, it has the same probability of going to S1 as it has to S2. And if it's small, that's what's going to do, one or the other. And if it's a bigger mutation, it has the same probability of going from the black dot to B1 or B2. So equal probability, equal magnitudes in either direction, no, independent of where the optimum is. This is a much more constraining picture of randomness than it seems like Darwin had in his head. It's the key to the argument that he's making. So there's the picture we have, and I added a third circle here, which is centered on the optimum. That's the smiley face. And the essential point here is that if the organism starts at X and it makes a small mutation, the probability is close to a half that it'll get closer to the optimum, that it's inside of the really big circle. Whereas if the organism starts at X and it makes a big mutation, the probability is about a third that it's going to improve its fitness. So you can see graphically how big mutations are less likely to improve things than small mutations. So his model entails the following, what I just said, that if a mutation is small, the probability that it's advantageous is greater than the probability of it's being advantageous would be if it was a big mutation. And as an extra thing, there's the mathematical concept of expectation. The expected degree of fitness increase is greater if the mutation is small than it would be if the mutation was big. And by the way, both of these expectations are negative because on average, a random mutation is going to move you away from the optimum. But you'll be worse off if you do a big step than if you do a small random step. Fisher thinks, I mean, he doesn't actually use these words, but in this passage, he seems to think that this geometric argument shows you that gradualism is correct. He says, large mutations occurring in the natural state would be unfavorable to survival. And as soon as the numbers affected attain a certain small proportion in the whole population, an equilibrium must be established in which the rate of elimination is equal to the rate of mutation. So Fisher, it seems like he's thinking of the size of mutation in the same way as you might think about the size of a tibia. Suppose in a population, having a really bigger tibia is really disadvantageous. So what you would expect is that the frequency of big tibias will decline, but But it won't go totally to zero because it'll be replenished a bit by mutations introducing genes that produce big tibias. So he's thinking about the size of mutation is working just like that. But there's a glitch here. In a simple model of tibia evolution, parents transmit the size of their own tibias to their offspring. But in Fisher's argument, the size of the mutation in the parent does not get transmitted to the offspring. What gets transmitted is the phenotypic effect of that mutation, not the size of the mutation. That's gone. It happens once, and then afterwards he's tracking forward where that what will happen to the resulting phenotype. And here's the beginning of a glimpse of where the problem is in Fisher's argument. Fisher's argument, in the first instance, is about the effect of a mutation of a given size on an organism's fitness. And that by itself doesn't answer the important question about the role of this picture in gradualism. Namely, it doesn't tell you how probable it is for a mutation of a given size to reach fixation once it occurs. There's nothing about fixation probabilities in the geometric argument. Here's a technical point about what we'll be developing more. So forget about the red things, about the expectation. And you want to start by thinking about the probability that a mutation, that M goes to fixation, given that it starts as a small mutation. Well, think about those circles. A small mutation occurs, and there are many phenotypic upshots it might have, all those different locations on the circle. And for each of them, you have to figure out what's the probability of it going to fixation, given that it's that phenotype that results for the mutation, or that one, or that one. And if you want to know what the probability of fixation for a small mutation is, you've got to average over all the possible phenotypic upshots and their different fitnesses. So that's why expected is on the left-hand side and also on the right. And so what we want to know is whether that's right. And what's totally irrelevant is this next inequality. That is, think of the expected fitness of a small mutation. What's the average improvement that you get from a mutation of some size? And then you ask whether a mutation that has that average fitness is going to go to fixation at all. So that's the second word where the mathematical expectation is embedded inside of that probability operator. And that's the wrong thing to think about if your question is really about how mutations, which may have different phenotypic upshots with different fitnesses, how a mutation of given size, what its average, its expected probability of fixation is. Now, there are other people out there, famous people, who have smelled a fish in Fisher's argument. There's something wrong here. I won't read you the quotes, but Matt and I think that they're right that there's something wrong with the argument. But where they think they found the mistake is really not right. They seem to be thinking that Fisher ignores the fact that a big mutation will sometimes have a super good effect, a super advantageous upshot. And he somehow ignored that when he says that small mutations always are better than big ones in terms of improvement on average. Well, he didn't miss that thing because he correctly noted, he took account of all the possible phenotypic effects and fitness consequences of a mutation of given size. That's what we were doing before. He was averaging over everything, the good news and the bad news. So that's not where the mistake is. Now let me hand it over to Matt.
So, yeah, so Fisher's argument is about the effect of a given mutation, of a mutation of a given size on organism's fitness, but it doesn't describe how probable it is for mutations of different sizes to reach fixation once they occur. And that's what we're going to do now. So, Kimura 1968 tells us that the probability of fixation of a mutant depends on its selection coefficient, and also on the effective population size. So I've just talked about a population of size n equals 10, so pretty small, and that just makes some stuff more obvious in the graph here. So suppose a mutation M occurs in the population that has a wild type W fixation. Then M can produce different phenotypes. That is, it can have different selection coefficients. Where S, the selection coefficient, is the fitness of the phenotype minus fitness of the wild type. So that's the wild type is going to be 0 here. And as we mentioned before, the average S value of a random mutation is always going to be negative. Okay. So we're looking at the probability of fixation given a selection coefficient. Now we can consider a big and a small mutation. Each of them is going to be centered on a negative value for S, so it's going to be to the left of this. And fixation probabilities for negative S values are all less than 1/2n. That means they aren't a lot different from each other. They're all pretty low, as you can see there. It gets a little bit higher when you get really close to 0. But fixation probabilities for positive values increase rapidly, as you can see. So the surprise is that a big mutation can have a higher average probability of going to fixation than a small mutation, even though big has a lower average S value. So you can imagine it deviates from that S value a long way on one side, a long way on the other. And since it deviates a long way on the right side, it gets you way up the hill, whereas a little difference getting you way out on the left side doesn't give you much of a penalty over that small one. So the reason that it's good for mutation to be bigger than small in this case, or bigger than very small anyway, is that it loses next to nothing by including those very negative S values. But it gains a lot by including some more positive values of S. And the nonlinearity of this Kimura's curve here is really key. If it were a straight line, you wouldn't get this. Okay. So the surprise, of course, is that a big mutation can have a higher average probability of going to fixation than a small mutation, even though that big mutation has a lower average S value than small. So what we're showing you here is in 2 dimensions, we have two dimensions of phenotypes. Thank you. 2 phenotypes, one along the bottom, one going along the edge there. You start at where it says present, and then the optimum is in the center there. This is just the same as the image we showed you for Fisher's geometric argument, but now we're showing Kimura's curve overlaid on that. So you can see the probability of fixation of all those points. And as you can see, the small circle, the small mutation there has a lower average altitude on the hill, you might say, than the big one does. So that big one has a higher average height and a higher probability of fixation. Okay. And another surprise, take a look at this. For 2 dimensions, the average size mutation that has the highest, or the size mutation that has the highest average probability of going to fixation is 72% of the distance from present to optimum. That seems like a pretty big size, much bigger than Fisher was hinting at. Fisher was hinting that smaller and smaller, infinitesimally small, is the way to go. So it's pretty big. It's at least a middling sized mutation. Now we've assumed, as Fisher did, that the relationship between phenotypic distance to optimum fitness and fitness distance to the optimum is linear. But that's not very realistic. A more realistic assumption that Orr uses is that that relationship is Gaussian. But so long as this relationship is monotonic and positive, there's going to be some middling sized mutation that has the highest probability of going to fixation. This is one thing that Orr talks about. He talks about this Gaussian relationship being the reason for the effect, but we've shown that even without that assumption, the effect follows. So he's missing at least part of the story. He's not telling us the entire story at the very least. And the upshot for gradualism is that for our definition of gradualism, that evolution happens mostly by the accumulation of large number of small mutations and rarely by the accumulation of a small number of large mutations. then Kimura's formula entails that the following claim is false, that the probability that M is now at fixation given M was small is greater than the probability that M is now at fixation given M was big. So that version of gradualism is mistaken. It doesn't settle a different gradualism question, which is the probability that M was small given that that mutation was small given that that mutation is now at fixation is less than, or should that be greater than? Should be greater than the probability that the mutation was big given that that mutation is now at fixation. So we can look at some new studies, or new within the past 20 years, I guess, since Fisher and since Orr wrote his paper. These genome-wide association studies, can they solve the problem? Can they tell us what to think about this? So what we want to know is whether the probability that the mutation was small, given that the mutation is now at fixation, is greater than the probability that the mutation was big, given that the mutation is now at fixation. And GWAS has determined for each locus how much variation in specified phenotypic effects there is among the genotypes at that locus. And GWASs often report that the loci studied that most of the loci studied have very small phenotypic effects. And that's also including the fact that these small that GWAS studies often can't detect very, very small phenotypic effects. So our question is it plausible that a locus that now has a small phenotypic effect score evolved in the past by mutations occurring that also had small effects? And that's kind of an open question we'd like to know the answer to. So does random mutation plus natural selection entail gradualism? Well, that depends, as we pointed out. If it's the forward version, the probability that M is now at fixation given that the mutation was small, then that's mistaken. If it's the backward version, then that might be true. Okay. So yeah, there we are. Thank you. So let's take some questions. Yeah, good.